Hello everyone and welcome back to another episode here of the Hidden Quantum Champions. Today we are looking into an Italian company which is called Think Quantum and is active in the space of quantum key distribution and random number generation. If this is interesting to you and if you want to understand what differentiates them maybe from others in the market, then stay tuned for today's episode as we are diving into Think Quantum. And with that, let's jump right into their website. So here we are, it says Think Quantum, and you see the bracket notation up here. There's also this little carousel here, so quantum random number generation, true randomness from quantum physics, the quantum revolution, next generation communication networks, that's on the key distribution right, and then quantum cryptography, pioneering quantum key distribution technology as well. Besides that, it says here, Think Quantum, be secure, optical and quantum communication technologies for cybersecurity. And then we see, similar to what we've also seen with other companies from that space, that there are some products down here. So it says Think Quantum SRL is a startup spin-off of the University of Padua, offering quantum-based technology solutions for cybersecurity and communication systems. It says QKD products and QRNG products, so random number generators and quantum key distribution devices, and these are rack size, similar to also what we've seen with probably competitors of theirs. So you can see they are made to fit into standard telecommunication racks. Now, besides that, there are also some explanations down here. So it says QKD systems, quantum key distribution between two or more locations via fiber, free space or hybrid channels. Then you see with satellites, so satellite QCOMs, space qualified and ground QKD systems for satellite to ground and inter-satellite communication. And then the quantum random number generators devices provide high bit rate and unbeatable pure random numbers. Who we are. So first, a reliable partner. Think Quantum SRL is a startup spin-off of the University of Padua, offering complete solutions for cybersecurity and communication systems based on quantum communication technologies. The recognition as a spin-off of the University of Padua grants access to resources like state-of-the-art labs, relevant IPs, and more. Officina Stellare SPA, major industrial partner, enables access to its scientific and optomechanical engineering skill set, backed by a solid international network and brand awareness in the space industry. The co-founders, Professor Paolo Villoresi and Giuseppe Vallone, with 20 years experience in the field and prestigious international positions within the scientific community, present the scientific milestone of the Think Quantum project. Based in Italy with an Italian shareholder structure, Think Quantum offers reliable European supply chain to partners active within geopolitical sensitive application, covering the full value chain from design and manufacturing to commissions for quantum key distribution systems and quantum random number generation devices. So here we see already some clear points. So one of them being, as a spin-off of the University of Padua, there's some access also to, let's say, the IP, which was mentioned here, and the state-of-the-art labs. There's also some connection to this Officina Stellare SPA, which is then for the space industry, some connection. So this is not only QKD and quantum communication on ground, but there's also some space element to it. And on top of that, we see here we have co-founders, professors from the university, and it is a very European company. So it's also interesting for, let's say, European companies that want to transmit information and make sure that this infrastructure is kind of European originated infrastructure, then this might be an interesting partner. And here is also the address. So it's a legally Italian entity. And with that, let's hop right into the technology. So this part is very nice to me because I see that there are a lot of nice drawings in here. So there's also a bit of creativity going into it, not just boring, let's say, graphs in here. So Let's go through it. The maturity of quantum communication technology represents today the best answer to the growing demand for security in communications. For example, an encrypted communication can be obtained through the exchange of photons, the light quanta, by exploiting quantum key distribution, QKD, or true random numbers can be generated by exploiting a random number generator. And that's the QRNG. Contrary to standard cryptographic solutions, the security of QKD is guaranteed by the laws of physics and not by computational assumptions. This represents a shift of paradigm since the development of mathematical techniques or the advent of the quantum computer will put these classical cryptographic methods at risk. And this is also targeting to this harvest now, decrypt later idea. I've talked about this in previous videos also as well, which is today you are collecting the data, and once you have the quantum computer, you run a derivative of Shor's algorithm on there, which can basically do prime factorization, which is the key to decrypt today's encrypted messages, because the prime numbers are considered to be safe because it's computationally complex to figure out the prime numbers that a number consists of, and that's why you can build an asymmetric encryption method based on this idea. Now, the QKD, the quantum key distribution, on the other hand, relies on a different hypothesis. There's always an hypothesis that's underlying. So, hypothesis in asymmetric encryption today is it is computationally harder to do, or it's computationally exponentially hard to do a prime factorization. So, if I give you a number 15, then you have to figure out that it's 3 times 5, and 3 and 5 are prime numbers, so they don't have integer numbers that they can be factorized into anymore. If I give you a very, very big number, it becomes very complex. If I give you just one of the prime numbers, or if I give you both of them, you can easily multiply them into the big number, but figuring out if you just get the big number, what are the 2 prime numbers, is exponentially difficult. So the idea is, if you take a prime number that is, or if you take numbers that are big enough and you multiply them with each other, it will take even the best supercomputer today longer than the existence of the universe to kind of figure out the 2 prime numbers. And that's why we think, or that's the mathematical concept, why these numbers are safe. Now, for the quantum key distribution, it has a different idea that is underlying. And here the underlying concept is that quantum mechanics is the correct description of the microscopic nature of the world or of the universe. So if that is correct, it is not possible to clone quantum information. There's this no cloning theorem. So you cannot copy a quantum information just like it is without destroying the information or without reading out the state. So if you now create an entangled pair of photons, for example, you could use that in order to make sure that nobody's eavesdropping in between, because you can figure out if somebody is kind of reading out your information channel, if somebody's intercepting it. And that's the underlying concept here. So the underlying concept is, if quantum theory is right and nobody has figured out a way to kind of clone quantum information, then this is kind of protected by this principle of quantum theory that you cannot copy the information. If this hypothesis is wrong, still somebody can eavesdrop and just get your information. But up to today, quantum theory is the most precise description of nature, of physics that we have by every measurement and by every mean. And that's why we think that it is a superior way to make sure that information is not being intercepted. Okay, close bracket, let's hop back into the text. So, typical optical elements used in QKD and QRNG devices are electro-optical modulators, polarization, beam splitters, fiber patches, single photon detectors, lasers, field programmable gate arrays, systems on a chip, analog to digital converters. The integration of these components allows for the realization of the QKD transmitter called Alice, so that's the one over here, the QKD transmitter Alice, capable of generating and sending quantum states according to an initial classical digital string provided by the QRNG, and the QKD receiver called Bob, which is this one here, which is able to read out the transmitted qubits and and store a digital string to perform the post-processing. So we see here Alice has this quantum random number generator. There's some control electronics in here, some optical components and the laser. Then they are connected via this fiber, which can be, I don't know, typically for these things up to 100 kilometers. Then on the other hand, you have again optics and control electronics. And in addition, you have the detector, which is then taking the signal from the optics, and the time tagger as well here. Now, coming back to the text, at Think Quantum, our team of physicists and engineers works together to realize quantum communication devices. Think Quantum offers QRNG and QKD solutions covering fiber, free space, and hybrid links to two-point communication, daisy chain, serial, and star network configuration. So these are, let's say, setups where you don't just have one of these pair here of devices, but multiple of those. For different reasons. Maybe you want to have a communication between different parties, more than just two. So then you will have this things like star network configurations. On the other hand, you might want to go for a longer distance because 100 kilometers might not be long enough. That is not so easy to scale because we are talking about single photons here, and there's always a probability that a photon can get lost. So it doesn't scale that easy over long distances. And that's why you need to have then this daisy chain or serial setup, I would assume. So Think Quantum devices are based on patented designs, and they can be easily integrated into current telecommunication networks. That's also something that has been pointed out by possible competitors already, that they are using the fiber that is already being used for telecommunication purposes today. So fiber-based QKD optical fibers represent the backbone of our modern communication systems with ubiquitous use from data centers interconnecting to long-haul links. In many cases, these links are used to transport highly sensitive information. In such cases, QKD could be an ideal solution to secure the data with the highest level of security. At Think Quantum, we developed QKD systems that reduce the resources required for its deployment, thus simplifying the integration of the system with pre-existing fiber telecommunication networks. Furthermore, Think Quantum uses patented state-of-the-art schemes that guarantee record performance in terms of source intrinsic qubit, quantum bit error rate, and temporal stability. These two components, they are also very important. Actually, they're free. There's another one which I think might be mentioned somewhere else. When looking at these systems, of course, you want to make sure that they work reliably. And what is being tested? So this is already undergoing. There are already companies, telecommunication companies, testing these systems today. And what are they looking for? So first of course, the error rate. So if I send one of these quantum information bits, how's the probability that this is correctly being received? How many errors do I accumulate over time? Because if only 50% of the data reaches, this is probably not a good system, because then you throw away half of the data that you generate. Which leads to the second point: how much data can you actually generate? How many of these keys, quantum keys, can you actually generate? Because if you want to make sure that the message is completely encrypted, you want to actually generate as much keys as you want to transmit data. So you really need to send them at quite high rates and quite many of those. And this leads then, of course, to the question of how many keys can you, or how many random bits can you generate with your quantum random number generator. And then thirdly is the temporal stability, which is also being pointed out here, which is after time, there are always changes in the system, right? You have temperature changes and whatnot. I'm not an expert in that. This is just my assumption. But these fibers, they are pretty long and they are substance to local environment changes. So at some point, the polarization that this fiber is causing might change, and the polarization plays an important role in this process of reading out the photons, or in the information that is covered in the photons. And therefore, you need to kind of counteract against this. So this is the question of temporal stability then, because these effects, they happen over long time periods. Then there's the free space QKD. So free space quantum communication allows for a point-to-point link between two locations without the need of an optical fiber. So now you're going through the, let's say, open space. This is the best solution for those locations that are not reached by the fiber infrastructure, or for those applications that require fast and or non-permanent deployment of a quantum communication link. It is also the solution for communications with moving platforms, such as drones, high-altitude platforms, aircrafts, and ships. At Think Quantum, we develop and deploy free space quantum communication terminals that guarantees full day operation. Our terminals can be used for one-way or two-way quantum communication, connecting two optical fibers or even over the air, thus avoiding trusted nodes among the peers and allowing compatibility with standard telecom quantum communication devices. So this is then going via free space. And one, let's say, extreme case of free space is then, of course, the communication with a satellite that is somewhere in the orbit. So that is long distance quantum communication requires to overcome the unavoidable loss of fiber-based implementations, which are therefore limited to few hundreds of kilometers. Since the technology maturity of the quantum repeater is still far away from concrete applications, so quantum repeater would be a system that can repeat the quantum information, which is not easy to build because of the non-cloning theorem, right? So the most effective way to expand quantum communication and QKD to the global scale is to use satellites and ground stations exchanging single photons. Space quantum communication requires the capability of designing and developing both the optical and the quantum communication payloads on the satellite side, as well as the competence to realize dedicated telescopes coupled to the quantum hardware on ground. So you see here this ground station and then the satellite. And of course, telescope here in this drawing is how we imagine a telescope to be like, but it could also be looking like a radio telescope. So this could also very much be a container with some type of detector, which is the telescope sitting on top. So you don't need to have this huge building, right? This is more for optical telescopes. Okay, thanks to the contribution of the lead Italian scientists in the context of space quantum communication and one of the most recognized professional telescopes producers in the world, at Think Quantum, we can effectively tackle the complexity of this new space technology. And finally, there's the quantum random number generator. This is, as we have seen, a relevant building piece, a relevant building block to this quantum communication. But it also has other areas of application, and I think this text is going to go into that in a second. So random numbers are an invaluable resource for many different applications, such as simulations, gaming, and security. In particular, they are fundamental building block for both classical and quantum cryptography. Indeed, their security relies on the unpredictability of the random numbers, and the privacy of the encrypted data is compromised in the random number generators are flawed. The majority of random number generators used today are based on deterministic algorithms, meaning that no matter how well the generator is designed, it will always be predictable. In the last years, the flaws in these random number generators have been exploited by attackers to realize important security breaches of different cryptographic systems. Quick step back on that. On your computer, you can generate random numbers. So if you're, for example, programming in Python, there's a random number library. You can just import that, and then you can say generate me a random number between 1 and 100. What actually happens is there is an algorithm in the background that is generating this random number. And this algorithm might collect various different information like the date, the time, some random seed phrase, whatnot. And you're basically inputting all of this information, and then you generate this random number. In fact, if somebody would know the algorithm, and people know the algorithm, then they can actually make use of that, and they can basically exploit this to, for example, if you're building some program that is somehow creating some encryption based on random numbers, then this can be exploited, and you can basically figure out what went into the encryption, and it's easier for you to decrypt. So this is an issue. The other point is if you're looking at simulation, for example, which is also mentioned up here, there's a whole family of simulations called Monte Carlo simulations, which rely on random numbers. So instead of simulating the whole system at once, you're basically randomly picking subcomponents of the system, and you simulate one by one until at the end you end up with something that describes the whole system. And for this, you need to actually be able to have random numbers as input, because if you're, for example, having a bias, like, I don't know, you are looking for the numbers between 1 and 10, and more of the randomly generated numbers are between 5 and 10 than between 0 and 5. So it's not a balanced function, not a perfectly balanced function. You will actually end up simulating only one part of the system, which will lead you to completely wrong results, because you need to be able to sample throughout the whole system in order to make good calculations with this method. You need to have an equal distribution of your simulation points over the whole system. There should not be any bias in there. So random numbers are very, very important. And the idea of these quantum random number generators is to use the probabilistic nature of quantum theory, of quantum systems, to actually generate random numbers. So here it says, on the other hand, a quantum random number generator exploits the intrinsic randomness of quantum mechanics to deliver secure private random numbers. The process at the heart of QRNG are inherently non-deterministic, and they cannot be predicted even if the full status of the system is known with absolute precision. Our technology combines high security standards with state-of-the-art performances at low cost, providing an optimal solution for a broad set of applications requiring the highest levels of security. Okay, quickly about the products. So let's hop into that one as well. So there's the QKD system, right? We've seen that before. It's called Quickie, I guess. The quantum key distribution platform by Think Quantum provides BB84 based quantum safe cryptographic keys with high quality in terms of security. So QRN 2-qubit direct stream, robust and reliability. The QKD platform includes Quickie TX, Alice, and Quickie RX, which is Bob, so the transmitter and the receiver. There's some brochure available here and some additional information about things like, for example, the key rate, so high generation thanks to the lowest Q-bar provided by the embedded IPONAC patented solution, and many other things. So EU27, as mentioned, it's a European company, so it says based in Italy, and Italian shareholder structure offers a reliable European supply chain. There are also technical specifications up here. So you see, for example, the secret key rate is 2.2 kilobytes per second, I guess, if I correctly interpret this here. And yeah, I don't know. I'm not an expert on that. I will not go through all of these details. Operating conditions are probably what you would expect in a data center. So 10 to 30 Celsius at 80 humidity, 80%. Relative humidity, non-condensing, and so on and so forth. We have as a subunit of this the quantum random number generator, which is TIG, the source of true quantum randomness by Think Quantum. And there, you also see high rates, high data rates, as again the European point, and of course also some other points. I'm not going to go through the details here. It says internal quantum entropy source is 2 GBps. A test compilation is also relevant, like how is this actually being tested, and many other things. I will leave that to the experts to look into this. I'm not going to read any tables to you now. Quickly about the history of the company. As per usual, that's probably also relevant. So Think Quantum stands on the shoulders of Quantum Future Research Group with 20 years long background in quantum optics, optical quantum information processing, quantum communication, quantum key distribution, and quantum random number generation. I'm not going to go through all of the details right here, but in 2003, so more than 20 years ago, University of Padua research project Space Q, Quantum Information and Communication in Space Channels, was probably the first activity in this quantum communication space. And then there are many, many different points which are being mentioned here, like first world demonstration of first, probably real world demonstration of the feasibility of single photon exchange from the AGSI satellite at 1,600 kilometers slant distance. Then you have some projects mentioned here in Padua. So this is all University of Padua related. Verification with photon space of the fundamental property of light known as wave-particle duality, first ultra-fast quantum random number generator in a source device independent framework, 2017, 2020, there's the kickoff of QASAR, quantum safe randomness, kickoff of the EU project, and then in 2022, Think Quantum, QKD, and QRNG systems are launched in the market. And there are many, many resources also down here linking to scientific publications related to this. Finally, let's quickly also check out the company. So what is the company standing for and who are the founders, like who's the team behind the company? So Think Quantum SRL is a startup spin-off of the University of Padua, established by Officina Stellare SPA and other academic founders offering quantum-based technology solutions for cybersecurity and communication systems. Think Quantum spin-off of the University of Padua. We've seen that, then the Officina Stellare, and then we have here the executive team. So we have president, vice president, CEO, and CTO. And if we look at the backgrounds, we see that we have on the one hand, let's say the technological side. So we have professor of physics here, but then we also have the business side covered. So head of business development and business management. So both facets are being covered here. There's also some mention here on key people and co-founders of the company with various different backgrounds as well. So very nice to see the faces behind the company. If you are still watching until this point of the video, please make sure to give the video a thumbs up. I would very much love that. È stato un piacere fare questo video con voi. Per me è sempre molto interessante anche fare dei video con aziende italiane. And with that, I'm looking forward to meet you in the next video again here of this Hidden Quantum Champion series. As always, make sure to stay hydrated and see you in the next one. Bye bye.